Hello everybody, in this video I will talk about local extrema, and let's start with the definition of the local maximum and the local minimum. Here we have a function of two variables, f of x or f equals f of xy, and f has a local maximum at ab if f of xy, the value of f at the points xy in some disk with center AB is less than or equal to the value of the function at AB. Then we say that f has a local maximum at AB, and the number f of AB is called a local maximum value. Local maximum value. Okay. And on the other hand, f has a local minimum at AB. For this time, if the value of function at the points xy in some disk with center AB is greater than or equal to f of AB for this time, then we say that f has a local minimum at AB. Okay, and the number f of AB is called a local minimum value. Okay, so these are the definitions of local maximum and the local minimum, and we will make a relation between local maximum and the local minimum and the first partial derivatives using this theorem here. F has a local maximum or local minimum at the point AB. If it has a local max or local minimum at a point, then either this first partial derivatives at AB equals 0 at the same time, okay, which means the first partial derivative of f with respect to x at AB and the first partial derivative of y with respect to y at AB is 0, or these partial derivatives do not exist, okay, at AB. So we will use this relation to obtain the local minimum and local maximum of the given functions. We won't use the definition during solving the questions. Okay, so I have some examples to you. Here we have an example for of surfaces for local minimum. Here we have let me write it like that. This point and this point are examples of surfaces for local minimum. As you can see, value of the function at these points is less than all the other values here, right? So this is the lowest point of the surface, so it is the local minimum here. And in this part we have just one tangent plane. It is something like that, okay? Just one tangent plane here. It passed through that point and it is tangent to that surface. So because of the first partial derivatives are 0. But here we may have more than more than one tangent planes here. So it says that the first partial derivatives do not exist. Okay, this is related with this case and this related with this case. Okay, and using the same idea, because let me try to sketch some tangent plane here. This may be the first one, and it might be something like that here also. Okay. This is the other one. Okay, so we may have more than one tangent planes here. Like in the absolute value function in the single variable case. Okay, there is no derivative here because you may sketch more than one tangent line. Okay, using that idea, you can imagine the tangent placed for this surface also. Okay, but for this time, in the single variable case, you have such a parabola. Okay, so here you have just one tangent plane, which is the x-axis. This is the single variable case, examples of the single variable case, but the idea is same. Here you are looking for the number of the tangent plane, tangent lines, but in the surface case, in the space, you should look at the numbers or number of the tangent planes. And here we have examples of surfaces for local maximum. Again, these points are the highest values here. So they around this point actually, okay, in a neighborhood of this point, whatever the neighborhood, all the time this number is the highest value of this function. So it is the local max here. But in this part, again, I have just one tangent plane. So it says in this case, the first partial derivatives are 0. But here we have more than one tangent line. So because of that, the first partial derivatives does not exist. Okay. Again, using the same idea, in the single variable case, I have such a parabola for the first part. So you have just one tangent line. And here you have something like that. It seems an absolute value function or such a function, okay? There is a corner here and you may sketch more than one tangent lines. And here you may obtain more than one tangent planes, but you have only one tangent plane here. So if you have only one tangent plane, the first partial derivatives are 0 at this point. But if you have more than one tangent planes, the first partial derivatives do not exist. Okay, let's solve some problems. But before, first of all, I will define critical points, saddle points, and I will give the second derivative test for the local extrema. Then we will use this test to obtain the local extrema of the given function. Okay, an interior point AB of the domain of a function, which means this point is belongs to the domain and it is not the end point. It is not on the boundary. Okay, an interior point AB of the domain of a function f of xy is called a critical point. The important point here is that if the first partial derivatives at that point are 0 at the same time, or one or both of those partial derivatives do not exist. At the point, okay. You will calculate the first partial derivatives and you should equate them to 0, and you need to solve two equations here. F sub x equals 0 at this point and f sub y at AB equals 0. If you can obtain such an ABs, then you can call this point critical point. Or if you can find a point at which these functions does not define, or the original function do not have a partial derivatives here, then you can also call these points as critical points. And we have also another type of point, which is called saddle point. A differentiable function f of xy has a saddle point at a critical point. First of all, it should be a critical point here, okay? Which means at that point, these first partial derivatives are 0, or one or both of those partial derivatives do not exist. If in every open disk with center AB, there are higher and lower points here, okay? Which means here it is neither, the saddle point is neither local max nor local min. Okay, you have such a point. If you have a saddle point, it is not a local maximum or it is not a local minimum, because you can find the points at which your function takes the values higher and lower than f of ab here. Okay. So this is really useful test for us. Using this test, we can directly decide the types of the critical points. First, we will find the critical points, and secondly, using this test, we can decide whether or not the critical point is local max or local min, or it is a saddle point here. So let's first of all look at the conditions of this test. Suppose the second partial derivatives of f are continuous on a disk with center AB, and suppose that we have this case in the definition of the critical point, which means we are talking about the critical points which makes first partial derivative 0. Okay, we have another case here. So it says that you can't use second derivative test for those critical points. Okay, if you have a critical point which comes from the first part, which comes from by equating the first partial derivatives to 0, then you can use second derivative test to classify them. Okay, that is AB is a critical point of f here. Okay, and then we will define some a, b, and c here to make calculations easier. A is the second partial derivative of f with respect to x evaluated at ab, and b is f sub y, the second partial derivative of f with respect to y evaluated at ab, and c is f sub x y, the second partial derivative. First of all, we evaluate the partial derivative with respect to x, then y here, and we will evaluate it at AB. So this is C. And I define a delta here. Delta equals AB minus C square. Okay. Then, using these, I can decide the local max, local min, and saddle point. If delta is greater than 0, and A is greater than 0, then f has a local minimum at AB. Okay, so here we have this. If you have that case, delta is positive and A is positive, you have local minimum. Okay. If delta is positive but A is negative, then f has a local maximum here. So delta is positive but A is negative, so we have local maximum. And if delta is less than 0, for this time f has a saddle point. At AB. So if delta is less than 0, we have a saddle point here. If delta is 0, so the test is inconclusive. Okay, the test is inconclusive, so you should use the definitions. Okay, so I will use this test to classify the critical points of the given functions, and we will solve some problems to apply this test now.